Assalamu alaikum wa rahmatullahi wa barakatuh. This is my first time actually recording in my school. So I'm not sure if I'm gonna get away with this, but inshallah we'll see how it goes. So my physics lesson is cancelled, that's why I'm even doing this video. And yeah, he's unwell, so he can't teach today's lesson. He literally told us half an hour before the lesson, so we all turned up wondering where he was. And yeah, he told us to go on chapter 24.1 for magnetic fields, but I got the A-level physics textbook and there is no chapter 24.1. So I'm gonna go on Kaboodle, and if I can't log in, then I'm just gonna do the first few pages of the magnetic fields chapter in this book, because I have no idea which one he's talking about. Unless it's this one, I'll check real quick. Oh, is this one? 24.1. Okay, I found it. Cool. Okay. Right, well I found the textbook then. So I need to open Kaboodle. Never really used Kaboodle either. Okay. Right, I have the textbook. Now what? Now I just need to read it. That's great. That is great, guys. Also, I'm using physics books to hold my phone right now, but I need the physics books. So. Okay, there I go. And then once I do this, I'm gonna get some statistics work done. Alright. Okay. Hopefully no one comes in because I'm not really supposed to be on a room alone. I'm inside a room alone without a teacher present, I don't think. Or maybe I am since I'm sixth form. I don't know, the rules are very strange. But yeah. Okay, today is Wednesday, the 20th. So we haven't actually started magnetic fields, which means I'm going to be learning this topic all on my own. So I don't know how that's going to work, but we will find out. Magnetism is a topic with a long scientific history, stretching back thousands of years. What is lodestone? Lodestone is a piece of magnetite. That's sick. Imagine finding a rock many years ago and then seeing that it attracted things to it. That would have been like magic, bro. Magnetite is a black mineral and is strongly attracted by a magnet and is important iron ore. Interesting. Alright. A magnetic field is a force field surrounding a magnet. What is a... Okay, gravitational field meaning. Because fields are essentially a region where non-contact force acts. What is a field? Physics. AQA. A-level. Okay, a field Oh, it's so quiet in here. I love it. I love quiet places, man. I was literally working alone in the lunch hall earlier. And then someone came up to me and was like, "Why are you working all alone here?" I'm like, that's the point, to be alone. Yeah, it's so beautiful to be alone. In silence, especially. Look how beautiful the lighting is. If only I could work in a physics classroom every single day. Anyways, a field is a region in which a point experiences... Also, it's warm too, even though there's snow outside. Experiences a non-contact force. Cool. Okay. And then a magnetic field happens not only around magnets, but also current carrying wire. So I'm gonna write that down. Bro. Magnetic field occurs around a magnet. Also, I need to replace my pen ink because it's literally like it's literally like empty right now, and it's not writing well. So I'm gonna do that now. Let's see if I have one in my pocket. Yes, I do. I have one in my pocket. That means I need to write on my hand ink refill. Ink. Because I need to remember to refill when I get home. Alright, cool. Alright. I just refilled that. Also, on the way to my physics lesson, there's a little kid who just shouted, "You're the guy from YouTube!" Oh my. So literally what my life has been reduced to now. Anyways, a magnetic field occurs around a magnet and a wire carrying current. Okay. And then the magnetic field of a bar magnet is strongest at its ends, such as the north and south poles. And then each end points when the magnet is free to align itself with the horizontal component. A line of force of a magnetic field is a line along which the north pole would move. Okay, I didn't know that. A line of force or magnetic field line is a line along which a north pole, and pole just means a point with north polarity, right? Pole is physics. Where's physics? So many definitions for pole. Bruh. A pole meaning A levels physics. It doesn't say. In which a north pole would move in that field. So a field is a region in which, if there's a point, there's a non-contact force acting on that point. A magnetic field occurs for a magnet as well as any wire carrying current, and then a line of force or a magnetic field line is a line in which a north pole would travel or would move in the field. Interesting, okay. The Earth's magnetic poles are known to drift gradually, and at the present the Earth's north magnetic pole is in northern Canada. What? And the Earth's magnetic field can reverse. That's really strange. The force on a current carrying wire in a magnetic field. A current carrying wire plus what? A current carrying wire placed at a non-zero angle to the lines of force of an external magnetic field experiences a force to the field. This effect is known as the motor effect. What is the motor effect exactly? Save my exams is so useful. I'm loading Save My Exams right now. Why do I have to log in? Bro. Okay. The motor effect. The motor effect is when a current carrying wire is placed in a magnetic field. Well, that's strange though, because the current carrying wire produces its own magnetic field already. Placed in a magnetic field and experiences a force. Yeah. And this is because the current carrying wire produces its own magnetic field, which interacts with the magnetic field of the bar magnets on either side. And those two interacting magnetic fields produces a force. Yeah, and that's literally it, bro. That is literally it. Cool. And look, this is what the diagrams look like. So this is when there's no wire involved, so it's just two parallel bar magnets. This is when there is a wire involved, and this is what it looks like without the bar magnets, and this is the two fields interacting. That creates an upward force on the wire, and that's why we use Fleming's right-hand rule or left-hand rule, I don't know which one it is, and it's like FBI, where F is force, B as magnetic. Wait, F is force, right? I think so. FBI. B is magnetic field, I is current. So force, field, current. That's what it should be. And then it's like this. This is the right or left hand rule. And if current is flowing in this direction, then the force is going that way. Okay. So force is going up, magnetic field is going. That means the current is going into it, okay. Okay, let's carry on with the textbook. When a current flows, the section of the wire in the magnetic field. So this is left-hand rule, where this is motion, so force, field, and current. So I did get it right. The force is greatest when the wire is at right angles, and 0 when the wire is parallel. Interesting. The magnitude of the force on a current carrying wire in magnetic field can be investigated using the arrangement shown in Figure 5. The stiff wire frame is connected in series with a switch, an ammeter and a variable resistor and a battery. The switch is closed and magnet. Show that the force F on the wire is proportional. I've never seen this experiment before. It's connected in series with a switch, an ammeter. I'm hungry, bro. Alright. The force on the wire is proportional to the current and the length of the wire. F equals BIL. Okay, that makes sense. But only at right angles. So, magnetic flux density is sometimes referred to as the strength of magnetic field. And to work out B, so we have the equation F equals BIL, right? So if we rearrange to get B, so B equals F over IL. F is force, I is current, and L is length of the wire. That means B, you can represent its unit as Newton or force per unit length per unit current. But at right angles, it only applies at right angles and a current carrying conductor. So the current carrying conductor, so in this case a wire, has to be at right angles to the direction of the magnetic field for the fields to actually have an effect on each other and interact, creating a force. If they're parallel, so the wire is going from the magnet to the other magnet, there will be no force because the magnetic fields are going in the same direction. In this case, so that means that F equals BIL, or the proportionality between F and L as well as F and current, only happens when the current carrying conductor is at right angles to the magnetic field. And the unit of magnetic flux density is Tesla, equal to 1 Newton per meter per ampere, which are just the SI units I told you about. Force, magnetic field, current. Current is east to west, field lines are north, so the force is towards me. That doesn't make sense. That just makes sense. Okay, so I'm going through a worked example right now. Straight horizontal wire of length, etc. Magnetic flux density and current. So we just need to work out force. It's just simply rearranging to get the subject in the equation F equals BIL. And then you have to state the direction of the wire. So we have a straight horizontal wire. Let's say the straight horizontal wire is like this. And then Fleming's left-hand rule, which I'm doing with my right hand. Force, magnetic field, current, all at right angles. So we're trying to work out force, and we have magnetic field direction and a current. So current direction is in this direction, so I'm just going to do that. So FBI current is like that, from east to west for me. And then north is just that way, and this is field line, east to west. Oh! That's east and that's west. Never eat shredded wheat, that's how I remember. So it's like this. And that's why it's pointing vertically downward. Okay, that makes sense now. Alright, time to actually do the questions. What are the questions? Are these the summary questions he was talking about? I need to check. I need to check what he posted on Teams. Also, do I have enough battery for this? Yes, I do. 83%. All right. Halfway through the lesson. Okay. Complete the questions in the book. Which questions? Summary questions for this. Yeah, I believe so. So that's so cool. Charged particles in a magnetic field. Looks like a picture of the sun or something like that. Oh, it's like dark, but yeah, so cool. Anyways. Dude, the next chapter is so much more complicated. The couple on a coil in a magnetic field. What is the couple? Rectangular current can coil. What the hell going on here? Come on. Sorry, sir. I was recording, so while you.
Apologies.
Noise. As long as you don't get in the video, because then I'll have to blur you out and everything, but that's fine.
I'll be fine.
Teacher came in the room. Why is it so dark? Okay, cool. Simple electric motor consists of a coil of insulator which spins. Okay, I'm gonna go. I don't understand that. So I am going to just attempt the summary questions. Okay. Question 1. The table below relates a force on current carrying wire which is at right angles to the lines of force of a magnetic field and current. Complete the table below by working out the missing data in each column. They should be fine, hopefully. Okay, 1A. So we have B equals 0.2 Tesla, I equals 3 amps. What? Dude, I and L have the same letter in this case. They just look exactly the same, I'm not even joking. And then force, so F equals BIL, so you just multiply them all together because they're already in your SI units, bro. This is light work. Imagine if all physics was this easy. Sadly it isn't. Okay, 0.2 times 3 times 0.04. That gives us 0.024 newtons. Then we need to work out the direction. So, force, magnetic field, current. Force is the one we're working out. Magnetic field is vertically down. Current is due north. So like that. Magnetic field, current, and then this is to the left. Force is to the left. Or you can say west. Yeah, you have to say west. Okay. Okay, 1B. So B equals 0.2 Tesla. I equals 0.04 meters. F equals 0.036 newtons. Using F equals BIL. L equals F over BI. So let's do that. Force, which is 0.036 over 0.04 times 0.2 is 9 over 2, which is 4.5. And since they're all in SI units, I can just put 4.5. Oh my days. We're actually working current. But it's fine because the calculation is the same. So 4.5 amps. And then we need to work out the direction. So magnetic field is still going vertically down, and then the force is going south, like that. Force is going south, vertically down, then this is current, which is what we're working out. Still to the west. Dude, I might have gone this wrong. Hopefully I haven't. 1C. Okay, so we have amps equals 3A. Well, current equals 3A, sorry. L equals 0.04 meters, F equals 0.024. And then B, we're working out magnetic field, so B equals F over IL. So 0.024 divided by 0.04 times 3. Since all in SI units, that gives us 0.2. 0.2 Tesla. And then we need to work out the direction, so due north, current, FBI, current is due north, that's right. And then force, which is this one, is due west. North, west is that way, so it's vertically down. Which makes sense because that's what we've been doing for the previous ones. Okay, 1D. So we have B equals 0.1T. Horizontal due. What does it even mean? Oh. Okay, so you don't actually know the direction. I equals 2A. And then L equals 0.04M. So working out F equals BIL. So BIL 0.1 times 2 times 0.04 is 0.008 newtons. And when you work out the direction, or do we have the direction? We have the direction, so that's east. We need to work out the direction of magnetic field. Okay, so FBI, current is vertically up, force is due east. How am I supposed to do this? Oh my god. Okay, F is due east, I is vertically up, and then B is horizontal due, what is this, south? This is east, never eat shredded wheat, so it should be south, due south. Okay. Dude, you have a lot of questions. I'm going to go to the next one, even if I might not be right. A straight vertical wire of length 0.1. Downward current of 4, so I equals 4 amps. It's all in SI units. Flux density is 55 millitesla, so 55 divided by 1000 is 0.055. Determine the magnitude and direction of the force. F equals BIL. So times them all together, times 4 times 0.1. 0.022 newtons, and then we have the directions. So vertical wire, a straight vertical wire. Straight vertical wire, what does that even mean? Downward current. That's due north. Okay, F. We have current. Current is downwards, vertically down. And then FB, this is north. Current is like that. Is this the only orientation? Current is down, field is that way. So what happens if we try to like invert it like that? That means field is down. Okay, so this is the correct orientation. Current down, field that way, which is north. And that means force is east. You know, I never got Fleming's left-hand rule when I was in GCSE. That's why I didn't do that well in physics, but... Okay, straight horizontal wire length equals... so 50 millimeters divided by 1,000 is 0.05 meters. And then... B equals 140 millitesla, which is 0.14 Tesla. Then we should have another variable, which is F equals 28 millinewtons. So 28 divided by 1,000, 0.02. That means we need to work out the magnitude of the current. So F equals BIL. That means I is F over BL. 0.028 over 0.14 times 0.05. So 4 amps, and then we need to work out the direction. We love working out direction, don't we? We have 20 minutes left. Okay. Horizontal wire. Okay. So FBI, B is vertically downwards. The force is due north, like that. So this is east. We'll see if I'm getting these right later on. Okay, question 3. Rectangle core of width. Why width, bro? Oh, now I really have no idea. Is there another equation that I can use? Is there another equation? I don't think so. The course placed. Or maybe I can. I'll look in the physics formula book, because there's no way they would give all that information for me not to use it. Oh, I still need to finish editing my daily vlog. Okay, I'll do that after I finish the physics. So, electric fields and capacitors. No. Oh, it should be in magnetic fields. Okay. Rotating coil. That's long. I really don't know for this one. Magnetic flux. What? So we have length. We have... Oh, we literally don't need any of the information given. Okay, whatever. So rectangular coil. In a uniform horizontal magnetic field. Horizontal magnetic field. Oh, I'm not that good at drawing, bro. Oh, this is a horrendous drawing. But it's physics, not art, so I really don't understand why they're making me have to do this. Oh, that's like actually bad, guys. Mamma mia. What is this drawing, bro? Okay, width. I know I'm supposed to draw width when it's 60 millimeters. That's actually thick. 6 centimeters. Why is the width of the coil 6 centimeters? Oh, width like this. Okay. Okay, width is 60 millimeters, length is 80 millimeters, 50 turns. I don't know what that means. What does that even mean? 50 turns. Coil. I don't understand what that means. How can it be rectangular and have 50? Oh, whatever. Oh, that's gonna be disgusting. Okay, 50 turns, all of that. Horizontally and uniform magnetic field. Right, sketch the arrangement and determine the force on each side of the coil. Okay, so we have L equals 80 millimeters, which is 0.08 meters. B equals 85 millitesla, 0.085. Then, do we have the current? We should. 8 amps. So that means force equals BIL, so 0.08 times 0.085 times 8, which is 0.0544 newtons. So we have, with its shorter side parallel. Why is there a shorter side to the coil? Oh, I think I might get it now. Maybe. So the current in a rectangular coil, it goes forward and then backwards, right? Like this. And this is a rectangular coil. So on one side it will put it that way. On the other side it will put it that way. And that's why it turns. So I just need to work out. So when the current is going that way, so FBI, I is current, and then magnetic field is going, how do I know which way is going where? How am I supposed to know, man? With you north. Let's do north on the left then, because that's what the diagrams are doing. N, S. So that means the magnetic field is going from north to south. That way, current is that way. Force is down on the left side. Which is the same as what they put in the diagram. Okay, I'll check the answer later. Question 4a. The Earth's magnetic field at a certain position, horizontal component of, so B equals 18 microtesla, which is 18 times 10 to the power minus 6 Tesla, and then a downwards vertical component of 55. Okay, so B horizontal and then B vertical is 55 times 10 to the minus 6 Tesla. So the magnitude of the Earth's magnetic field it says magnetic field, but it just wants magnetic field density, right? Which is just Pythagoras 18 and 55. So magnitude 18, I need to square both these. 18 to the power times 10 to the power minus 6 squared plus 55 times 10 to the minus 6 squared is 5.79 times 10 to the power minus 5 Tesla. Or you could write it as, is it 58 microtesla? That doesn't sound right? 18 squared plus 55 squared, then square root, really is 58, right? Okay. The magnitude and direction of the force on what? Okay. 4b. So we have the B equals 58 microtesla, or more precisely equals 57.8705 microtesla. And then we have F equals, we're trying to work out F. L equals 0.8 meters, I equals 4.5 amps, F equals BIL, so we have the magnetic flux density times 10 to the power minus 6 multiplied by 0.8 times 4.5 I got syntax error. How is there syntax error? Uncertain, 10 to the power minus 6. There is no syntax error. What are you on about? I'm just going to show you my calculator. There should be no syntax error. Also, it's 10:49. Am I in the villa next? If so, then I'm really cooked. I'm in the... Oh, it's break next, so it should be fine. Okay. F 57.8705 times 7 minus 6, 0.8 times 4.5 is 2.08 times 10 to the minus 4 newtons. Then when you work out the vector, on a vertical wire of length carrying a current of 4.5 downwards. So a vertical wire, and then the Earth's magnetic field is going outwards, right? FBI, magnetic field. So downwards is vertically downwards. The magnetic field of the Earth bro, I really don't know. The magnitude of the Earth's magnetic field at this position. What? How can the magnetic field be acting in opposite directions at the same time? Doesn't make sense, bro. Doesn't make sense. I can hear my friends from the other side of the room, bro. Anyways, force magnetic field current. Well, current is downwards. Vertical wire. We just need to work out where the magnetic field is. Is it here? Or is it like... Because the current has to be downwards, so it's like a 360-degree rotation of this. Which means the force is either north, east, west, or south, depending on where I position the magnetic field. So, dude, if it has a horizontal and vertical component, horizontal and vertical like that, but the vertical component is oh, I think I get it now. Okay, so the vertical component of the Earth is downwards, and the horizontal component due north. So downwards, and then north is that way. So it's going like this way. It doesn't really make sense. Let's just make it go north. So current down, magnetic field north, force is east. Time to check our answers, guys. Ooh. Okay, that's nice. Right. I'm tired, bro. Where the answer is? Absolute temperature. Cool. Okay. I hope it gives the working, but it probably won't. Wait. It smells nice. The book smells nice. Oh, okay. So chapter 24.1. Dude, it really smells. Oh, that smells amazing. Okay, 24.1. Okay, 2.4 times 10 to the minus 2. Yeah, to west. Let's go. 4.4 times east to west. Let's go. 0.2 Tesla vertically down. 8 times 10 to the minus 3 due south. Okay, that's wrong. Wait, yeah, it is due south. Yeah, let's go. Let's go. Okay, I'm a W, right? 22 million. Oh, I accidentally cut the video because of my alarm. I have to merge those two videos together somehow. Anyways, yeah, there was only a few seconds between the last clip where I just cut off and then now. 4 amps due east. Yeah, why do I have, today is Wednesday. I should have set the alarm for tomorrow, so I did that incorrectly. Because I have an orthodontist tomorrow, and I have to leave in the middle of the school day all the way to go to city centre and then cycle back. Very fun. Okay, west to east. Short side 0, long sides 2%. So this is the one. Short side 0. 2.72 vertically, so I got that one. So the Earth's one is Pythagoras, and then 6.5 due east. I got that wrong, but I got due east right. I don't know how I got that right. Okay, 6.5 times 10 to the power minus 5 and due east. Okay, so that's a smaller value. I think they just did 0.18. 18 times 7 minus 6 times 0.8 times 4.5 gets you 6.48 times 10 to the minus. I get it! Do you guys get it? So, we were told that the vertically down component of the Earth's magnetic field is 55 times 10 to the minus 6 Tesla, right? But the current, guess what? Guess where the current is also acting in? Or the direction of the wire. So, the direction of the wire is the same as the direction of the current, right? And the direction of the wire is in the same direction of the vertical downwards component of the Earth's magnetic field, which means it has no effect on it. And it's only the horizontal component of the magnetic field that will result in a force on the wire, which is why you only do that multiplied by F and L to get your multiplied by I and L to get your force. That's so cool, man. That's so cool. Okay, that's sick. Right. The only thing I don't understand is the diagram and why I got 2.72 wrong. But short sides is 0, yeah. So there's no force. So we have a rectangular coil. On the long sides, so these long sides, there is a force acting upwards or downwards, and then there's an opposite force on the other side too. But on these ones that are like perpendicular to these parallel magnetic plates, there is no force because they're parallel to the magnetic field. Well, I don't understand. Why is it 2.72? That is my question. My question. This was a good session though. Allahumma barik. Allahumma barik. Do I multiply that by 50 or something? I do multiply it by 50. Interesting. Okay, I'm going to ask the physics teacher that came in just now on help for that question because I'm really excited to understand the reasoning. So you work out F equals BIL as normal, as then you multiply it by the number of turns. So I really want to understand why that happens. And then I'll get work done on my statistics homework for a test this Friday, which is literally 2 days from now. And then I will finish editing the daily vlog because I forgot to add like the little clips in the intro. Right, awesome. This was a good study session. Let's go. Assalamu alaikum.